Welcome to the pre-recording of MCS 481, course on computational geometry in the fall of 2023. So this is the first lecture in three parts. So there is first a slide presentation, and then I will show a brief demonstration of the software that we're going to use. The slide presentation itself is divided in two parts. So I will talk about the course, what is the goal of the course, and then I will start by describing our first problem, our first geometric problem that we're going to consider. So the algorithms in this lecture are still not that advanced, so we will mainly focus here on getting the problem understood. All right, what is actually computational geometry? Imagine the following problem. You are on your way to work and you really need a shot of coffee, so you want to get the nearest coffee shop. But of course, you are walking in an urban environment, so you cannot go straight through the buildings, so you have to avoid the buildings. And you can imagine that you are sending your robot or away. So this will involve maps and will involve the overlay of maps. So you have the geometric locations of your position versus all the coffee shops. Um, that will be solved by the notion of a Voronoi diagram. So a Voronoi diagram is here defined. We will spend 1 week in this course on Voronoi diagrams, so it is an essential topic. It will involve also the avoiding of obstacles. So we will also uh, talk about those issues in the course. So the first three bullet points here are an indication of the importance of geometry to applications. This is not an applied geometry course. The applications will be used to motivate the geometry problems. So what is computational geometry? It is the study of algorithms and data structures to solve geometric problems with the focus on exact computations that are asymptotically fast. So starting to read the definition backwards. So we are interested in algorithms that have a linear or a quasi-linear cost. So most of the algorithms will be similar to sorting. There is also the focus on exact computations. So that's why I indicated that uh, this is not really a applied geometry course because data in the real world is often only known with limited accuracy. But that would lead us into numerical analysis. And that's the reason why the focus is on exactness. Although we will address also today the issue of robustness. How do your algorithms behave if the input is changing? So computational geometry. Geometry is key here. We will solve geometric problems. It is an algorithms course as well. In that sense, computational geometry is part of computer science, which studies algorithms to transform data. So the data comes from geometric problems here. Um, It is also part of mathematics. So it is so this is in the curriculum of mathematical computer science. So whether you come from computer science or mathematics, you can emphasize both. So you should be strong in both areas. But in this course as a student, you can of course focus on your strengths or on your weaknesses, what you would like to improve. All right, I'm following this textbook here. So this is the textbook by 4 Dutch authors. So that's published by Springer Verlag. That's also why it is called the Dutch book often. It is in terms of level, it might be considered a graduate level textbook, and this is a senior level master course. So in some sense, the textbook, I really like it, but it might often be a little bit difficult. It covers many of the standard topics. So here we have the topics of the first 11 chapters. Today we will introduce the convex hull problem in the plane. At the end, we actually go into convex hulls in 3 dimensions. So the solving of the 3-dimensional convex hull problem, or actually also the n-dimensional convex hull problem, was a major result in computational geometry. So you see, Voronoi diagrams are quite central. You can check the posted list of topics on the course website. We will do this chapter, so somewhere in the middle or around week 9 or week 10. So I hope that by then you're not too overloaded in the semester. But we will cover then also the relationship with triangulations. We will, you see the guarding of an art gallery. So we will, I've seen that this proof, how many cameras do you need to guard an art gallery? That is proof from the book. So a course on making mathematical proofs can also use this problem. So this is the an emphasis on the mathematical part. But then you see also the geometric data structures. We are living in an age of data science, so how querying a database, so organizing data, these are typical computer science problems. So we will go very thoroughly through the first 11 chapters. So computational geometry is very huge, and we will go very briefly through the last chapters. So this course can be driven also by projects. If you are taking this as a graduate student, you might be interested in a specific topic. So it is an algorithms course. So we do have an algorithms course, MCS 401 or CS 401. That's the official prerequisite. So this course is on both of our tracks. It is on the computational track and it is on the algorithms and theory track. So you could see that 401 is a solid algorithms course. 481 is actually, if you like, a redoing of this course. And for students on the computational track, 401 is not required. So this is why I would say that if you are on the computational track, you haven't taken 401, you are welcome in this course. So, there is the mathematical part, so understanding the geometry. Mathematics, when it's taught very badly, is you see it or you don't see it, and you have to see it within seconds. That is not the case, so you can study mathematics very systematically. In the goals of these pre-recordings here and the goal of the lectures, uh, are actually that you can understand how to do the exercises. So in the exercises, so there is always a part that is geometric, so you will have to make drawings, that is to guide the insight. And there is also an algebraic part, so where you can write something out. So algorithms are central. So the second goal is the understanding of the fundamental algorithms. There is the software CGAL. CG stands for computational geometry. AL stands for algorithms. So this is a standard free and open source library that we will be using. Uh, this is not a programming course. I will emphasize this again. We will also, this is not the type of course where you have to do all your computations by hand. So all exams and will be open book. You will be, it will be necessary that you can use software, that you can use a computer. Since this is also a course attended by graduate students, so you can substitute the final exam by a final project. So instead of, then we could also mix it. Some students do the final exam, some students do a final project presentation. There is homework. So here I'm counting now 3 projects. So the 3 projects will be counting for 200 points. The midterm and the final exam are 300 points, and then the homework is 100 points. So it kind of 50-50 in between the work that you do, projects and homeworks, and then the exams are testing your knowledge. Homework is important. I want to see for me also as a diagnostic, what kind of questions can I ask on an exam? Um, okay, CGAL, and perhaps I should have had this open, but let me do this anyway. So I will go to the website, hoping that my internet is actually not that good. So I will wait for the website to load. So I was indicating that this is not a programming course, but looking at software is a great way to learn about programming, and also we learn about geometry. So the textbook gives algorithms in pseudocode and suggests that they are in sufficient detail for you to implement them. So in that sense, one could still see this course as a programming course, but it might be very frustrating and take a very long time if you have to get through fully working code. So that's why we will always start with the code. So let me see, the website is loading, so here it is. So you can see the geometric modeling of aspects, so the notion of triangulations. Subdivisions are used a lot in computational dynamics, computational visualization. There are many applications. If you go to the download section, then you can see that the software is available on all platforms. I will say something about the installation. It is a C++ library with bindings to Python. And I think that the Python bindings may suffice for this course. So in the third part, I will give a very brief demonstration on how to use the software. So you can use the software even as you are not very confident in your programming skills. Python is a very high level language, scripting language. So if you know a couple of commands, even you can get a lot of use out of this. On I have installed CGAL with an Ubuntu package manager. I'm presenting this pre-recording on a Windows laptop from the Windows subsystem for Linux part. In that sense, I can kind of combine the best of both worlds, of all worlds. The Python interface installs both with pip and conda. So whenever I install Python, I also install NumPy, SciPy, Matplotlib, Jupyter. So if you have sufficient space on your disk, I hope that this is the case, then there should be no problem to install it with a good um, network interface. So CGAL itself, I do not want to overwhelm you too much in this course. Probably I have already done so by showing the entire table of content. So CGAL is extremely extensive, and you are welcome as one of the activities to browse what is available in this collection. In this semester, I'm also teaching a software course, so I find that CGAL is also an excellent example of a very nice library, very nice software project. Okay, let's go now into the mathematics. So definitions are important. With the exercises, you try to get the insight, the intuition with drawings, but it's very important also to write definitions that are necessary. If we have um, concepts, and the important concept on this slide is that of convexity. What do we mean by convex? Well, let us first look at 2 points. So a point, so 2 points define a line segment, and that line segment is our first example of a convex set. So all the points in between those 2 points are belonging to the set. So we say that any set, and it should not be necessarily something that is a polygon, can be a sphere, can be a circle, a disk. A set is convex if and only if, so this is a two-way street. So complete characterization is for any 2 points that you pick in the set. For any point, so here you see the algebraic definition of a line segment. So this is a very brief definition. I started to talk about a line segment. One can draw any 2 points and draw the line segment between them. Algebraically, you have the coordinates of the points. So here x and y indicate and now actually I should probably start drawing something. So I have a whiteboard behind my head. So I have 2 points, x and y. So this means I have x1, x2 here. I have y1 and y2 there. So these are the two coordinates of the points. And the line segment consists of all points in between. And algebraically, this can be defined as all combinations that you can make, all convex combinations, as they say, for any t inside the interval 0, 1. So this is a definition of a line segment that in some sense can be used to extend the first definition of convexity. Okay, so now let's try to turn this into a problem. So the problem on the slide, the second definition here, is for any set that you have, you can construct the convex set. That is the smallest convex set that contains the set. So it's the intersection of all the convex sets that actually contain it. The book uses the image of points as nails sticking out of the plane, and you imagine a rubber band and you let that rubber band snap around the points. So you stretch your rubber band and then you let go, and your rubber band will have the minimal length surrounding all the points. So that is the convex hull. So I'm in halfway my slide presentation, 20 minutes in this pre-recording. This is actually the central notion of convexity. So here let's now look at the convex hull problem. So any algorithm should start with an input-output specification. I give also the input-output specification is important for writing, so for finding also the right notation of all the main characters in your problem. So writing a good input-output specification is very important as programmers as well. You can also look at the example that is here. So we have on input a set of points, a set of coordinates. For the Python programmers, they are tuples. And we have on output ordered list of points. So the picture, so we have the algebraic coordinates, but then we have the geometric picture. So I picked a triangle. So the origin is over here, 0, 0, 10, 0, 10, 10. And then there are two internal points, 4, 1 and 6, 5. They are in the strict interior of the triangle. And the output consists of the point 0, 0, 10, 10, 10, 0, and then actually you can go back. So we are working around the clock. So by default, counterclockwise is also fine. But here we have the clockwise interpretation of the order. So you are computing it's a sorting problem essentially. So we are ordering the input points, but also omitting points that are not strictly necessary, which are not the corner points. We are ordering in such a way that we can interpret, and we actually also computing both the corners and what they call the edges. So edges are line segments that connect two points on the definition of the convex hull. So the convex hull is the entire triangle, so it's the inside as well, but we can define the convex hull by these 3 points. In the convention that 2 points that are next to each other actually span an edge. So this is formally written down here. Note we have n points on input, m points on output. So the m is less than or equal the original n. We have a finite collection of points. So that is the problem. And you can see that I've already used the word convexity again. I have implicitly defined an edge. An edge is a line segment. Line segment is still behind me. So let's redefine the notion of convex hull now. So this is again now going back to the mathematical side. So what is the convex hull of a set of points? So here I'm using the sequence of points, a list of m points. We are defining the convex hull. So the convex hull is now, it's an entirely discrete problem. The first definition was actually rather, so the first definition is still here. So the first definition was rather short. The first definition is now being made much more suitable for computation and for algorithms. So it's turning into a discrete problem as well. We have added the extra restriction. We have added the extra restriction that the point set is finite. So that was not in the first definition. Okay, so the first exercise, so let me spend some time on this. So you have to show that the new definition, the convex hull, that is equivalent to the definition that we started with. given the fact that we actually take a finite set now, adding that restriction and also looking at a set of points. So what is the key notion that connects the two? What is the idea that is required here is another definition, and that's the definition of a half plane. So perhaps I can try to draw, so here I'm having a line segment, so 2 points, and I drew the line segment here. So every line segment you can extend it to an entire line, and then you can work the with the half plane. So I can actually start shading this. So the green side is everything that lies here, and if you can kind of imagine a little bit what I'm trying to do, I'm not going to continue this, but the green actually extends everywhere at the same side of the line segment. One line segment extended to a line defines a half plane. A half plane is convex. If you have many line segments, you have many lines, you have many convex sets that you are intersecting. So the key connection between the definition as a convex hull given by points would be to focus at the intersection of the half planes. So the exercise 1 is kind of critical to understand the notion of convexity. Linked with line segments, half planes. So you can think of triangles. So in solving the exercise, you have to do two things. You have to define what is a half plane, and then show that the intersection of a finite amount of half planes is again convex. So you can prove by induction. One half plane is the base case. A half plane is convex. Then you have the intersection of two convex sets is again convex. So there are two ideas in solving the exercise: a formal definition of a half plane and then making the connection between the edges and the half planes. Spelling everything out could go to a very long description, but in all the exercises, if we have a couple of paragraphs and a couple of ideas, that will suffice. All right, this gives us actually the first algorithm. So we know that if we are computing a convex hull, we actually are computing also the edges. And the property of the edges is that all the points lie at the same side if we extend the line segment to a half plane. And we can therefore compute the convex hull by computing all the edges. So we have a finite set, we take all pairs, and we keep the pairs if we see that all the points lie at the same side. So in some sense, this is also geometrical. Of course, it is a geometrical algorithm. So how would you do it if you have, say, 5 points in the plane? You would start by drawing candidate edges and then seeing that some of the edges don't work because there are points on both sides of the line segment. So only those that lie at the same side, those edges where all the points are at the same side, should be retained. And then there is a last step, the sorting. So these are the ideas of the algorithm. What do we actually now mean with at the same side? So if you look into, perhaps a drawing is again very appropriate here. So we can look at edges as vectors. So one of the prerequisites is actually also vector calculus, and I hope your knowledge of vector calculus will come back. So if you look at the orientation of the edges, so we oriented them clockwise in the example. So either all the points lie to the left or they lie to the right. How could you interpret this as well? So the exercises are kind of connected. So in the previous exercise, we defined the half plane. Here, actually, you can relate algebraically, so you can define a half plane as a linear inequality. So an alternative description of the convex hull as the intersection of the half planes is the listing of all the inequalities that a point should satisfy for a point to be inside the convex hull. If you have an inequality, then evaluating the inequality will result in a number that's positive or negative. The positive or negative can be connected to left or right. So there is, in solving this exercise, also a definition that is needed. What is the meaning of same side at the left of the right, and how does that relate how you orient your edges? Which point comes first? So if you draw your edges like this, or if you draw them the other way. All right, so that is the idea. The exercises that are following now are kind of so here is the algorithm now formalized in pseudocode. So the pseudocode, any algorithm is consisting of a sequence, a loop, and a branching statements. So these are the three primitives that we have. Every loop has an initialization, so the output will be an ordered set of edges. The edges are actually interpreted as consecutive points in a list. So we enumerate all possible pairs, and then for every possible pair, we go through all the points in the set, excluding those 2 points that we picked in the pair, and we check whether it is at the right side. So why is that now important? Are we going to work counterclockwise or clockwise? Here, this is interpreting now exercise 2. At the same side, you should pick sides, which actually, so both interpretations can be correct if you work clockwise or counterclockwise. It depends if you sort in ascending or descending order. It's similar. Okay, so this is our first algorithm. Any algorithm in the proper sense of computer science is an algorithm that is consisting of an unambiguous sequence of instructions that can be executed. So in a way, this is probably fine enough for us now, but in order to turn this into an algorithm that works on a computer, you will need to have somewhere a primitive to work out this instruction here. And this is where vector calculus comes in again. So that's the exercise 3. You can also solve it by determinants, as suggested in one of the exercises in the book. You can also, and you have taken vector calculus. In vector calculus, you can work with the angle. So you have the vector P, Q, and then you have the point R. And then actually you define the other vector. And you have the angle that you can compute. So that gives you an idea. So that's the picture, very crudely drawn, the picture that corresponds to the idea. So you can use the formulas that you have seen in vector calculus to compute the angles between two vectors. So what you actually want is that this angle here is properly is at the right. It means that this angle is properly defined. Okay, so let me consider now the last step. Why do we have the simple last step? Construct the sorted list. So how does quicksort apply to this? Well, it's a statement. Sort is actually a basic step. That's why we list this as one instruction. Come up with any sorting algorithm. How does this apply here? Okay, n log n. So important, we are interested in fast algorithms. So typically this means that algorithms that scale very well if we have a very large number of points. N log n is what they say quasi-linear. If you double the size of the input, then the time is also about doubling. Not here quite with n log n, but the log n factor is very, very small compared to the n. Okay, cost analysis. So when you look at a code, you should be able to say what is the order of the number of operations. So we enumerate all possible pairs. So we have n, the number of points. So we have n possibilities for the first point, n minus 1 possibilities for the other point. So for the q. So this gives us n times n minus 1 pairs. So that means that you have n to the power 2 if you expand it. The minus n is not going to make that much of a difference. So also asymptotically fast. So we look for the leading factors in any polynomial expansion. So we have then the determining at the right side. So we have to look at the n minus 2 points. Now, deciding whether a point is at the right or not is an exercise, but is an operation that is a primitive. What is a primitive operation? A primitive operation can be done in constant time. And for the purpose of asymptotically fast algorithms, constant time can be ignored as just a constant. In practice, this is in general not the case. So we have the three steps in the algorithm: enumeration of all pairs, deciding whether a point is at the right of the pair, and then we have the sorting. So the if test is inside the for loop. And the for loop is actually a double loop. So that means that we have the if statement that is executed n minus 2 times n to the power 2. It actually gives us a cubic cost. Cubic cost n to the power 3 is acceptable if you solve a linear system. It's not really acceptable if you are dealing with problems that are essentially boiled down to sorting. So in some sense, this is our first algorithm. You have seen sorting algorithms before, and the worst sorting algorithms somehow were quadratic. I don't think you have seen cubic sorting algorithms, but this is in some sense a cubic sorting algorithm. Um, ha ha ha, mathematicians trying to define algorithms. So that is also why it's very important in this lecture to get the mathematics right first. So that's actually the main point. This is what we would call a mathematically correct algorithm, but certainly not an asymptotically fast algorithm. We can do a lot better. All right. Um, I will conclude with pointing at two degenerate cases. So the degeneracies, they can come from exact inputs. So here you see a lattice polytope. In working with algebraic geometry, you work with curves, and you can look at the exponents of the monomials that occur. So here all the points 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, they all lie here on this line. So we have an edge that will be repeated multiple times. So we have to find a way to deal with, we had very strict at the same side, but you can also have a point that actually lies on the extension of a line segment or lies at the interior. So you see, we glanced over this when we were defining our algorithm. If we consider coordinates that are known with limited accuracy, we may get into even worse situations. So it could be, like in here in this case, that we cannot decide whether a point lies to the left or the right. So sometimes we decide when we look at it this way or that way that it should be there or it shouldn't be there. Sometimes we may have too many edges that are reported or too few edges. So working with approximate coordinates is even harder, a subject in numerical analysis. What should your working precision be relative to the accuracy of the input? That's a difficult question. All right, I will switch to the demonstration part of this pre-recording. What are the recommended activities? Browse the website. If you do not have a sufficiently good computer to work with, let me know. We can do something about this. But I'm actually assuming that you can install Jupyter Lab. So all the exercises will be collected in a Jupyter notebook. I will post Jupyter notebooks with the examples. Install the Python interface. I'm assuming familiarity with the Python language. Think about the solutions to the exercises. I have given hints on how to deal with them. Try to write them down. So this is a first step. And the exercises might be a little bit expansive sometimes, but I'm looking for some major ideas. So consider also the exercises in the textbook, and I will announce which homework problems will be collected for grading. All right, I'm running this in a Jupyter Lab notebook, so that means that I can have multiple tabs open. So the purpose of this Jupyter notebook is to do a very quick introduction of the software that is available in the Python ecosystem. So whenever I install Python, I install also NumPy, SciPy, and Matplotlib. So here you see how you can use the Convex qhull algorithm. So in the next lecture, we will see a proper algorithm, an asymptotically fast algorithm. There is qhull. qhull solved this problem in great generality. It is available in scipy. So let me illustrate how this works. So I do this here on a random collection of points. Whenever you execute this, you will see a different collection. And I spoke of approximate input, so everything is approximate here. So when we compute the convex hull, we get the vertices, and this is set up to work with any dimension. So actually we have simplices. So here you see the edges. Actually, here now you see them if they are plotted. So again, what is important in this is that you get the concepts. We have the notions of the points that span the and you see randomness is always quite good, because here you see that if you look at the points, we actually do have already some degenerate cases here. But the algorithm that we will cover in the next lecture is robust enough to deal with that. All right, so this is a check on your installation. Um, so in some sense, in a software course, if you have to work with in an application with polygons, then this is a great start. Then you can also do this with CGAL, and I was actually quite in a rush when I prepared this, so I just copied and pasted from the Python interface. So in some sense, this is pure Python. So you see we work with lists. CGAL exports the definition of a point. So I make a list of CGAL points, points in the plane, point underscore 2. We are defining the input. That's just the list of these CGAL points. And then I apply the convex hull 2 method, underscore 2 method. And here you see the points that are printed here. Also, this is a check on whether your installation worked. Okay, two different software environments all together in one Jupyter notebook. I'm in a Jupyter notebook here, and let me launch Launcher. What is important is that we also have a terminal window here. So in this terminal window, I can illustrate a very basic C++ program. So in a C++ environment, I installed this. So this is on an Ubuntu within the Windows subsystem for Linux. It's quite, so if you took a data structures course, so in our data structures course, we use C++. If you are confident with C++, then please look at the code. So this is the sanity check also on the installation. So I used the standard package installers, which should be good for our course. It's not the very latest version of CGAL, but it should suffice for this particular course. So that is one of the programs. Here you see the equivalent of the making of the convex hull. And this is the convex hull I've shown on the slides. So we had a list of points, 0, 0, 10, 0, 10, 10. So I placed the corners of the triangle first, and then I had the two interior points. So C++ can often be a little bit scary, but here you see that once you are used to the framework that, or all the data structures that CGAL provides for you, then actually it's not quite long to do. So if you are using in the project the C++ version, we typically start from an example. So here this is an example for making the convex hull of these points. So I define the input list, and in some sense it's even shorter than the Python version that I just showed, just one statement, an array of 5 points. I will define here the convex hull, which is here defined as a CGAL object, pointer, also actually a point to pointer, and I can actually print then the results. So let me show how this gets compiled. So it is array convex hull to one must link with GMP. So GMP is the arbitrary multi-precision integer arithmetic. So let me run this as well. So this is the example on the slides. So the triangle spanned by the points 0, 0, 10, 0, and 10, 10. Properly sorted. So actually, on the slides, I was using the clockwise order. Here you actually now see that CGAL uses the counterclockwise order. Okay, I'm over time. So I hope that this lecture was not too overwhelming or too confusing. And I hope that the important notion of this mathematically that we have introduced is that of convex hull. So that's the important concept. In the next lecture, we will see our first asymptotically fast and robust algorithm to solve this problem. If any problems with installation occur, please do not wait till the deadline for the project is due. Do not wait till the midterm is there and you have no working versions of everything. Please try to settle this as soon as possible, certainly before the end of the first week of classes.